Welcome to this video series, Using Response Surfaces in DesignXplorer. In this video, Part 1, I'll set up and generate a response surface. I have a problem that is already set up, solved, and ready for further analysis. It is a structural model of a hook. The inputs are thickness, depth, lower radius, and angle. There are two outputs. One output is solid mass, and the other is safety factor minimum. I want to minimize the mass of the hook while still achieving a safety factor of at least 1.1. Here, note that the safety factor is under 1.1, which means that the hook will fail. Now, I could easily predict that increasing the thickness will result in a larger cross-section, and therefore reduced stress and an increased safety factor. Things become more complicated, though, when more inputs are added. For instance, how does the combination of depth, angle, and lower radius affect the stress? And how can we adjust all of these to achieve our safety factor while still minimizing the weight, that is, our material costs? The goal is to find the exact combination of parameter values that will give the lowest mass while meeting my minimum safety factor requirements. A response surface study will help me to do this. The first component in my response surface optimization system is design of experiments, or DOE. This one has already been solved, but I'll take a look anyway to review my parameters and design points. Here, I can see my inputs and the ranges I've specified for them. I need to consider these design constraints on the inputs. I ran this DOE with default values, a DOE type of central composite design, and a design type of auto-defined, which optimizes the DOE based on the number of input parameters. I can look at the values for my outputs using the design points versus parameter chart. I'm going to look at the design point values for the output safety factor minimum. You can see the design points here along the x-axis and the safety factor minimum parameter here along the y-axis. If I check the values for each design point, I'll find that 11 of the 25 points do meet my minimum requirement of 1.1. Here, you can see that design point 13 has the best or highest value, so I might think that's my best choice. But now I'll also add the output solid mass. It shows up here along the y-axis on the right. Now you can see that design point 10 has the best or lowest value. For this design point, though, note that the safety factor minimum has a failing value. The problem gets even more complex when I consider all the inputs and their ranges of variation. Even if I know of one combination that meets my requirements, there may be an optimal combination that I'm not even considering. In this case, the DOE has fallen short of predicting the behavior between the samples. It's difficult enough to use the interpolations to find an optimum with only one or two outputs. It becomes even more difficult with additional outputs, or when you consider the inputs as well. The purpose of the response surface is to interpolate the values in these multiple dimensions. Now, I'll go to the Response Surface tab. There are a lot of different response surface types, but here I'm keeping the default, standard response surface full second-order polynomials. For this type, only manual refinement is available. I'll also specify that I want to generate 3 verification points, and I'm going to make sure that min-max search is enabled. For min-max search, I'll keep the default of 100 initial samples and 3 starting points. Now, I'll do an update to generate the response surface. With the response surface updated, note that the outline has been updated with results. Under Response Point, you can find a set of charts. I'm going to select the response chart which is available in 3 different display modes: 2D, 3D, and 2D slices. I'm going to select 3D to show you the 3-dimensional response surface that's been generated. For now, I'll just note that this chart allows you to see how a selected output parameter changes in response to variations in 2 input parameters. For example, this particular response surface shows the output solid mass with regard to the inputs, thickness and depth. This video has demonstrated how to set up and then generate a response surface. This concludes Part 1 of this series. Join me for Part 2, which will focus on interpreting our response surface results.